Since the room is full, I got the signal to start with the talk a bit early. So thanks for sticking by to the end of the session. I hope it'll be worthwhile for you. I'm Matei Zaharia. I'm a grad student at Berkeley working on large-scale data parallel computing, and I'm also a Hadoop committer. I've done a bunch of work on the scheduling code in Hadoop in the past. And I'm going to present Spark and Shark, which are open source infrastructure we're developing at Berkeley to speed up data analytics. So I'll just start with a quick overview of each one. So first of all, Spark. Spark is the one that's been around longer. I'll start saying what it is by saying what it isn't, which is it's not a modified version of Hadoop MapReduce. A lot of people ask us, oh, how did you modify Hadoop to do this stuff? Instead, the goal of the project was to develop a separate parallel computing engine that can run faster than MapReduce, using some similar principles, though, and to see what we can do with that. And the ways in which it's faster, there's two main things. So one thing is Spark provides primitives for in-memory computing, which help if you have any kind of application that reuses the same data over and over, including interactive data mining or iterative algorithms. And the second thing is that it's not just a map and reduce phase. It actually builds a graph of arbitrary operators, and you get some speed-ups and optimizations by supporting that. And given these optimizations, Spark can run up to 40 times faster than Hadoop MapReduce in sort of real-world applications, not just benchmarks, but actual people using it have seen this kind of speed-up. At the same time, though, the goal of the project was to be as compatible with Hadoop as possible from the beginning. And we do this through compatibility with Hadoop's input and output format APIs. So we can access any storage system and storage format that Hadoop supports, including HDFS, HBase, Amazon S3, all that stuff, sequence files, Avro, using the same API. So anyone who writes a plugin to have input from their system into Hadoop automatically has input into Spark. Shark is a newer project, which is a port of Apache Hive to run over Spark. And it is an actual port of Hive, so it's compatible with Hive's existing query language, UDFs, SERDES, all that stuff. And it has some of the same speedups that you see in Spark, of order of magnitude speedups by running on this faster engine. And this whole line of work started in about 2009, and Spark has been open source since 2010. I just wanted to give a bit of background on where we're coming from. And Shark itself is a project that started within the past year and was just open sourced. An alpha release came out in April. And it started as a research project at Berkeley, but since we open sourced it, we've seen quite a few people actually start picking it up and using it for interesting applications. So some of the users are other universities, such as Princeton, and companies such as Foursquare, Cloud, Conviva, and others. And we started hosting a regular Bay Area user meetup. There are 200 members signed up for that, 500 watchers on GitHub. So the community is expanding. So in this talk, I'm going to give an overview of both projects. So I'm going to start with Spark, the programming model, and then I'll talk about a few things users have done with it. And then I'll talk about Shark. I also want to give a short demo of Shark. And then in the last few minutes, I want to talk about the next step we're adding to the platform, which is research we're doing right now, which is support for real-time stream processing inside the same engine. So let's start with this. So why did we want to develop a new programming model, not just go with MapReduce for Spark? We saw MapReduce was extremely successful, and it made it really much easier to work with data at large scale, which is really awesome. But as soon as people started using it, organizations loaded a lot of data into Hadoop. They wanted to do some applications that MapReduce as a model wasn't well suited for. So in particular, we looked at two types of application. One is more complex analytics algorithms, which usually have multiple passes over the same data. These are things like machine learning. These are often iterative algorithms or PageRank or stuff like that. And the other one is interactive queries. You load all this data. You want to ask some questions and explore it interactively. And the problem in both of these is that both of these require essentially running multiple MapReduce jobs over the same subset of the data. And so they need very fast data sharing between these. Or at least that's something you can do that will make them significantly faster. But when you look at data sharing in MapReduce, the only option you really have is to put the data in the file system, put it in HDFS or maybe in HBase or a storage system with similar properties. So say you're doing your iterative PageRank at the top. You read some data, you run first iteration of PageRank, it's a MapReduce job, and then you write all your state back to HDFS. It gets replicated 3 ways. Now, next thing you do is you immediately read that back into the next MapReduce job, do some more crunching, and write the state back out. And similarly, when you're doing interactive queries, all the queries have to do an HDFS read. And these reads are actually very slow. So because you have several things going on. You have data replication, you have serialization, you have disk I/O. And in fact, we measured that in a lot of Hadoop applications, they spend more than 90% of their time doing these things, like just talking to the storage system, not actually computing anything. So in Spark, what we add is the support for in-memory computation, where you keep the state in memory as Java objects across the jobs. And it's actually not replicated either. We do fault tolerance in a different way without requiring replication. And so you go at the speed of the actual computation on the in-memory objects, not at the speed of HDFS. And this can easily, memory as a whole is easily 10 to 100 times faster than network and disk. And of course, avoiding serialization also helps. So in more detail, the way you write programs in Spark is you manipulate these collections called resilient distributed data sets, or RDDs. And the way to think of this is as a bunch of Java objects that are spread out across your cluster. And you can choose to have some RDDs cached in memory across multiple MapReduce steps. And then you get different operations on these: map, reduce, join, filter, all kinds of higher level operators. And these collections also get rebuilt automatically on failure by the system, so you don't have to worry about that. The way we expose this to the programmer is through a programming interface in Scala, which gives you a nice language integrated API. I'll show what that looks like. And it's also kind of cool because you can use it interactively from the Scala console. If you're not familiar with Scala, it's basically a higher level language for the JVM, but it's compatible with Java. You can call any Java library. So let me show you a bit of what this looks like. Here's some Spark code you might type in interactively. So here we're going to say we have a big log file in HDFS, for a web application, and something's going horribly wrong, and we want to load just the error messages from the log file into memory and search for different patterns. So this is going to be our cluster over here, and we have basically a master node called the driver and a bunch of workers. And then here's some code that we can type in to do this. So the first line of code here is telling Spark to load a text file in HDFS. This gives us our base resilient distributed data set, or RDD, that we're going to transform. So this is just all the lines of text in the file. Next thing, we apply some operations on it. So for example, we want to filter out only the lines that start with error. These are the error messages in the log file. So the code in red there is Scala syntax for a function literal or a closure, kind of like a lambda in Python. And you can call, you can have more than one line of code, and you can call any Java library you want in there. So it's really arbitrary Java code in there. This gives us back a transformed data set. We might do more operations. For example, maybe these are tab-separated fields, and we want to pull out field number 2, which is the actual message. This is how you do that in Scala. And finally, we tell the system to cache just the messages, not the whole file, but cache just the messages in memory, because we're going to be asking many queries about them. And so what you can do next now is ask a question about it. So far, all the operations have been lazy. They don't actually get evaluated yet. But the first time you do one of these things called an action, it will actually go and execute the plan on the cluster. And so here we're counting how many messages begin with foo. And Spark will figure out where the data is in HDFS. It will send tasks. Workers will process their data, give back some results. And each worker will also build a cache of the partitions of cache data sets. It's built along the way. Next time we do a query on this, maybe foo wasn't the problem, but bar was, the job scheduler is now aware of what's in memory on the different nodes. So it's going to launch tasks with memory locality. It's going to hit the cache and give you back the results much faster without having to rescan the whole file again. And of course, you can do more than just like filter and count. You can do other operations on this. So to give you a sense of the impact this makes, one of the tests we did was a full text search of Wikipedia, which is about 50 gigabytes on 20 machines. And this takes about 20 seconds with on-disk data, or with Hadoop, it takes about half a second with Spark. So doing these full text search of 50 gigabytes. And that's the advantage of, first just the speed of memory, but also of just having the Java object sitting there in a form that's ready to process right away. And for fun, we scaled this up as well. So we scaled up to a terabyte on 100 machines, where we can do a full scan in about 5 seconds, compared to 3 minutes for Hadoop. Something else the model provides that I'm not going to talk about too much here due to lack of time is fault tolerance. So Spark remembers how it built anything that goes into its cache, all these partitions of the messages, by keeping track of the graph of operations that build it. We call this a lineage graph. And if it ever loses a cache like this one, it knows that, OK, I can take block 3 of the file and run this filter and this map on it again to get back that block. So it automatically recovers all these collections on failure. To give you an example of a iterative application, this code here is a machine learning algorithm called Logistic Regression. And you don't really have to understand the algorithm. This is something you use, for example, to build a spam filter. It's to do classification, basically, between labeled objects. But just to see the structure of the algorithm, it's basically a bunch of MapReduce steps on the same data. So the way this works is, first we load the raw data, and in this Spark code, we're going to convert maybe lines of text into point objects and keep them in memory. And then you start with this random initial value for the parameter vector you're trying to learn. This is like your spam filter, like a line that separates the spam from non-spam points. And then you do these MapReduce steps where you do some math. And the point of this is you have a bunch of MapReduce jobs that do a slightly different function. Each one uses the current parameter W here, but they're all on the same data. And finally, this is basically a gradient descent. So it's an optimization process that's going to converge to the final value. So this is what this looks like. You could write this in Hadoop, too. And here's how it performs. So this graph here compares the performance against the Java implementation in Hadoop. And basically what we see here is, as you have more iterations of your loop, Spark does better and better in relative terms. And this is because Hadoop always takes the same time per iteration, about 2 minutes, most of which is actually spent just reading the data and munging it into a form that it can process. And Spark, on the other hand, takes about 3 minutes for the first iteration, but then it takes only 6 seconds. And I think this is like maybe one of the most surprising things for us to take away from here is that you can write these kinds of algorithms in MapReduce, and they'll scale linearly. It will look awesome. You add more nodes, it will go faster. But the cluster is still spending 95% of its time not running your code. It's doing this other stuff to talk with HDFS and read the data. And so you're basically still spending 20 times more resources than you should be to do this. We support a bunch of operators beyond what I've shown so far, beyond map and reduce. So these are just some of them. We've tried basically to add the kinds of things that are common in Hive and Pig and these kinds of higher level systems, and support them efficiently out of the box. So you can read more about these online. And we also have a few other features in the engine. Just have one slide about these. These features can actually improve performance even if your data is not in memory, even if you just use Spark to run once, one pass on disk data. So one of the ones is this. I talked about general graphs of operators. So if you have map, group by, and then sort, that's map, reduce, and reduce. We'll do that as a single job, and which is faster than putting the intermediate result in HDFS. We have hash-based reducers, which is faster than the sort in Hadoop. And we also have control over data partitioning. So if you partition your data in a certain way across operations, you can lower the communication. Like you can keep data about the same object on the same machine across jobs. So the graph at the bottom shows a test we did with PageRank. And if you just implement PageRank in Spark using just the basic operations, it's about 2, maybe 2.5 times faster than Hadoop. But if you also use controlled partitioning to keep the information, keep the data about the pages partitioned in the same way across the jobs, you get another factor of 3 speed up. Okay. So that's an overview of Spark itself. A little bit about what people are doing with it. So here are some of the users of Spark already. There are actually a bunch of others that I haven't put the logo for up here. And over time, this group has grown. I put together a list of some of the applications. So we see people using the system in a variety of ways. One way is to do essentially the kind of analytics you do with Hive and Pig, but to do them faster. So Conviva, for example, is a company that does large-scale streaming video and analytics on that, that's been using Spark in production for, I think, about a year now, and has replaced about 33% of their Hive jobs with Spark. And they've been using it to run these things faster. Another interesting example is Quantifind. So Quantifind is much more of a real-time company. They do predictive analytics on trends using data from social networks and other data feeds. And they've been using Spark as an in-memory, like a persistent compute engine. So they basically load new data every few minutes, merge it with an in-memory table they computed before, do some machine learning calculations, and then they have this web UI for analysts where each time you do a query on the web UI, it actually launches a Spark job in the background to answer that query. Foursquare has been using it for some log analysis, and in Berkeley we have a few large-scale machine learning projects using it, including traffic estimation and spam classification. To dive into just a couple of these, this is one of the results from Conviva. So this is one of the reports they ran for their customers that basically tells the customer in different geographical domains, like by city, by country, by state, how are people responding to their video stream, what kind of quality are they getting, and so on. And they wrote it in Hive at first, and it ran as about 40 different Hive queries that did group bys on different fields, basically. You just had a lot of different combinations of group bys, but they all worked on the same subset of the data relevant to this user. And that took about 20 hours. Then they realized that actually a lot of the time spent in this Hive job was basically wasted on each iteration. So the job only used a couple of columns in the data set, and it only used rows that passed a specific filter. And it also kept running these different group bys over the same data. So they decided to just write that job in Spark and load the relevant data into memory once and then run with it. And when they did that, they reduced the runtime to about half an hour. So most of that half hour is actually loading in the data, and then you do all these group bys very quickly, and you're done. Another application, this is more of a machine learning one. This is Mobile Millennium project at Berkeley. They do kind of the equivalent of Google Maps using crowdsourced GPS data. So what they do is they receive these points every minute from cars of people who are running a mobile app, or from, for example, taxi cabs with GPS on them. And using them, they see how fast the cars are moving along each sort of road segment, and they infer the traffic condition on that road segment. So they can get traffic conditions at a fine granularity on roads that don't have sensors, where things like Google Maps don't actually provide information. And the picture there is just showing over the course of a day how they're accumulating data points to do this. But basically what this looks like is this expectation maximization, or EM algorithm. And they run this using Spark on up to 160 nodes. And basically the result is that it does scale well, and it's enabled them to do much more complex models in real time to process this data. So it actually, this scaled almost linearly to 160 machines over here. Okay, so that's just a quick overview of Spark. So next, I also want to talk a little bit about Shark. So Shark is the new thing that's basically new for this Hadoop Summit. When we started Spark, we were excited to have this high-level programming interface, but we also knew that a lot of people don't want to write code, and it would be very attractive to put other interfaces on top of it. And the most natural one to do first was Hive. So Hive is very popular. It gives you SQL, which lots of people are familiar with. But Hive is really not great at all for interactive analytics, because even the smallest MapReduce job you run on Hadoop takes 30 seconds to a minute. So it's really not a great interactive environment. So we wanted to see, can we just provide this SQL on top of Spark? And the way we did this is by actually porting Hive, which lets us retain as much compatibility as possible with what's already in there. So this is what you have in Hive today. There are kind of three pieces. So there's the meta store, which keeps track of which tables you have in your cluster and what the schema is. There's the client. The client has a command line interface or JDBC, and it takes a bunch of SQL and comes up with a query plan and launches it as a bunch of MapReduce jobs. And then the execution engine is MapReduce on top of HDFS. What we changed here is the stuff here in blue. Basically, we only changed the client. So Shark works with an existing metastore and existing HDFS. And what we change is we add this cache manager to let you load some data into memory. And we changed the planning to actually use the Spark operators instead of writing a sequence of MapReduce jobs. And we've also started hacking on the query optimizer to take better advantage of the features in Spark, and also just to do better query optimization to begin with. We've done a couple of things in there. And then we run over Spark. And the cool thing about this is it runs over existing Hive tables, existing metastore. You just run it as a separate client. You don't have to change the way you're managing your warehouse in order to use this. To do the actual caching, we paid a lot of attention to how to do in-memory storage of Hive data efficiently. And we ended up with essentially this column-based storage. So it turns out, as I was saying, serialization is high overhead. So we can't just take the bytes that are in HDFS and stick them in memory and hope to achieve a high speed up. And it also turns out that if we expanded all these bytes to Java objects, like the Hive record object, there's a lot of bloat. So there's a lot of overhead. For each Java object, there are a bunch of pointers and bookkeeping in the JVM. And what we do instead is this column-oriented storage, where if your record has a bunch of fields, like say an int and a float and a string, we keep arrays of ints, arrays of floats, and an array of characters, that is the different strings. And this gives you, at the end of the day, it gives you a size that's compact. It's similar to the on-disk size of the Hive data, but it's also about 5 times faster to access than the serialized data. OK. And how do you use this? We're still working on, on the actual interface to use this. But right now, the way we have to use it is through a special create table statement. So when you do create table as select in Shark, you can give it a bunch of SQL, for the thing you want in your new table. If your table ends in underscore cached, we're going to cache it in memory. And and then further queries on that will be fast. And then you can run any HiveQL on it, as I said. And we're actually also working to let you call it from Scala. So you can call Shark from a Spark program and intermix SQL and, say, machine learning, stuff like that. And there is an alpha if you guys want to try it out. I'll talk more about this, later. So how it performs, we have just a couple of pictures here, but the result is it's essentially similar to Spark. So this here is showing one simple query from the Hive benchmark, which is just a text search on a data set. And we have Hive at the bottom, which took about 200 seconds. Shark without caching, which is just running on the on-disk data. It's a little bit faster because our startup overhead is less than Hadoop's. So it is a little bit faster. And then Shark with the cache data is almost 20 times faster. And next one here, this is a more complex query. You don't have to look at what exactly it's doing. It's also from the Hive benchmark. It does a join. It does a group by. It does some sorting. So it's actually like 3 different MapReduce steps and the limit. And in this one, actually, the Shark without caching is substantially faster than Hadoop. And this is because of the hash-based join that we're doing, and because of some optimization we're doing with limit. We push down the limit operator a little earlier. And then Shark within memory data still gives you a significant speed up. The speed up is less here just because the job does more communication. So it's bound by the speed of the network. OK, so let me try to actually show you this thing in action, if the internet works. OK, so what I have here is a cluster on Amazon EC2, 25-node cluster, where I set up Shark. And OK, so SSH connection is still working. So this is the Shark shell. I loaded a bunch of tables related to Wikipedia into this thing. And what I'm going to do is just a very simple text search query and compare Hive against Shark. So first thing I'm going to do here is go into Hive mode. And you can actually do this. You can switch at the console and go into Hive. And then I have this table here called pages, which is all the pages in Wikipedia. And it has their title and their text inside the page. And I'm going to just count pages that match a pattern. OK, this is the narcissistic query. How many pages have Berkeley in the body? And let's run this using MapReduce. So this is just Hive itself, running the way it's doing. It's connecting to the cluster. It's gonna run this stuff. So we'll just give it a bit of time. Yeah, and it's going on. I think this will take about 30 seconds, by the way, if you're wondering. OK. Yeah, it's almost done now, just the last few bits. And this table is about 50 gigabytes of data, by the way, just so you know. OK, so yeah, so it took about 38 seconds. So yeah, it's cool. We were able to work on big data, but it's not exactly interactive. So next thing we're going to do is let's try the same query in Shark. And first, let's try it without caching anything. And you can go back into Shark mode and then run the same thing. OK. So Shark is a lot more exciting in terms of log messages. They go by. So you'll just sit by your computer to watch these finish. And yeah, it's going. And OK, this only took 11 seconds. And this is because in Hadoop, there's just a ton of overhead in terms of starting a job. Hadoop was, it was designed for big, like multi-hour batch jobs. So they didn't care much if it takes like 20, 30 seconds to actually start a query. So this is OK. So let's now also load the table in memory. And we'll do that through the create table statement. OK, so page is cached. And now it's running a job just to load that stuff into memory. Yeah. OK, and now let's run the query on the page is cached. So same query, but page is cached. Yeah, there you go. It took about 2.5 seconds. So being in memory does help. And final thing, just to show I'm not just pre-computing this thing for Berkeley, you can ask other queries you want. And this is the one I always ask. So Berkeley, by the way, lost in this flurry of log messages is the answer, which is 80,000 pages containing Berkeley. And let's look at Stanford. And Stanford is only 69,000. So there you go. OK. OK, so I have a couple more minutes left. And in that, I just want to talk about what we're doing next. So this stuff is less ready. So Shark, there is an alpha. And by the end of the summer, I think there'll be 1 or 2 new releases. And we want it to be like really easy to use. This next stuff is going to take a little longer. But basically, this is what we're looking at. So when we started Shark and Spark, we did all this in-memory stuff because we saw this emerging use case of interactive and multi-stage applications that really needed fast data sharing. Well, it turns out another use case that benefits from fast in-memory data sharing is stream processing. So for example, imagine you're keeping counters of like people who visited different pages on your site, and you want to just keep a big in-memory table and update them as people are clicking things. Or for example, say you're doing like a spam filter, you want to update it in real time. So can we add stream processing to Spark? So the Spark streaming project extends the engine to support streaming computations. And essentially, the way it does it is by using the existing engine to run each streaming computation as a bunch of small batch jobs. And we're aiming for sub-second jobs here. So you'll get like 1 or 2 seconds of latency maximum. And keeping state in memory between these as the distributed data sets I talked about before. Basically, the idea here is you'll be able to write a streaming job in terms of these high-level operators like map and reduce. We have new operators like reduce by window, which is a sliding window that does incremental computation as stuff enters and exits the window. And this will compile down to the existing Spark operations, and the state will be in memory, and it will be automatically fault-tolerant for both state and computation. So you can just write your application and have it run. And more importantly, this will also integrate seamlessly with the existing features in Spark. So you'll be able to connect, say, a Scala interpreter to the running program and ask interactive queries on the stream state. And you'll be able to join, say, a stream with batch data that you computed offline. Just an early result, the current prototype we have can handle 42 million records per second on 100 nodes. And these are 100-byte records. So it's actually 4 gigabytes per second of data at sub-second latency. And when we've compared it to other open source streaming systems, it's competitive. It's often actually a lot faster than the existing ones. And it provides these fault-tolerant guarantees that they don't have. So the hope is for an alpha of this to come out by the end of the summer. Let me know if you are interested. OK, so to conclude, Spark and Shark are open source projects designed to speed up interactive and complex analytics and to give you an alternative to the Hadoop MapReduce execution engine that does a bunch of more interesting things under the hood. To try it out, we check out sparkproject.org. There's a bunch of documentation, and it's easy to run. We provide easy scripts to launch it on EC2, run it locally. And we're also soon going to be able to run on Yarn, which is the Hadoop 2.0 resource manager. So we want it to be very easy to launch this. We have a user meetup if you're in the Bay Area. And we're also going to have a training camp at Berkeley in August on how to use these two technologies. So again, let me know if you're interested in that. Yeah, thanks. OK, any questions?
Yeah, I was just curious what happens when you run out of RAM on your cluster, because there is a limited amount of RAM. If it's easy to create tables that are cached, you can quite easily run out.
Yeah, so Spark is designed to degrade gracefully when you run out of memory. Actually, this is the first backup slide I have. And the idea is we're going to keep some of the data in memory and some on disk. And we have different cache replacement policies, so you can prioritize the important one. And all our operations are scan-based, like MapReduce. So they work pretty efficiently with on-disk data. We're not going to go trashing around. And so we're working, we want to make this seamless for you. You shouldn't care how much memory there is in the cluster. Yeah.
Twofold question.
Yeah.
First of all, my compliments on the great achievements, and unfortunately, it hasn't been done in Groovy, but Scala. But OK.
OK. Well,
if you want
to add a Groovy API, you should.
I would love to. Yeah. Second part is internally Hive is monstrous static kind of blob of code, right? Mm-hmm. Shark suffers from the same, or it's completely.
So Shark is, it inherits Hive's, I guess it's not a super modular design. So it would be cool to build a kind of a separate engine. We decided to go with Hive because we were afraid people would say, oh, maybe it's not compatible. But it would be cool to do something more separate.
But basically, that means that I can throw Shark on top of existing Hive stuff.
Exactly.
Awesome.
Yeah,
great.
That's the trade-off, yeah.
How I can sign up for training camp?
Good question, yeah. So we haven't actually announced the camp. We haven't put a website for it yet, but if you sign up for the Spark mailing list or meetup, or you visit this page, we're going to post it there. Yeah, I'll make sure it's known when it goes on. Yeah, it'll be like in August.
I have a question. So I saw that you have to explicitly specify that you want to retrieve data from cached or non-cached.
Yeah.
Is there a plan to like make it adaptive? So if there is enough RAM available, then,
yeah, absolutely. So like one of the things we're looking at from a research perspective is how to do caching automatically. And it's actually kind of a hard problem because not only do you have to decide I'm going to cache this, but when you get a new query, you have to tell that which cache table should you use for this query. But we're going to try to do that. Yeah.
And so second question. So is it so on a multi-tenant environment?
Yeah.
If people are doing
Right.
like how?
Yeah, so multi-tenant environment, right now, each instance of Spark actually has its own separate amount of memory. So it's really designed for like a per session thing. What you can do with Shark, I think the first step will be you run a Shark server, and there are many tenants, and they each share the same tables. They just access it through JDBC. So that'll work for that. We're also working to share data across Spark applications, not just Shark, by having basically the cache be external to the system.
Thank you.
All right,
Okay.
My question was kind of partially answered earlier, but I was sort of wondering about compatibility with Hive, sort of from a feature perspective, as Hive continues to develop.
Yeah.
Will Shark diverge from that, or is the goal to sort of keep it compatible?
Yeah, it's a good question. We'd like to try to keep it compatible. I think it will require some engineering work, and it would be pretty cool actually to work with people in the Hive like development community to maybe factor Hive in a way where this can be done, because we don't do crazy changes inside it. We plug in at one layer of the query planning stuff. But yeah, so this is a concern for us too. Yeah.
So there's several different changes that you've made to Shark as compared to Hive and MapReduce, right? So it's not one monolithic. You've columnarized it, you've transformed it, you've put in memory caching, you have a different execution architecture.
Yeah.
Can we expect at some point and you have the limit optimization, which probably should go back to Hive anyway. But so the question I have is, can we expect a paper or some summaries about how they break this up? Because the ColumnOriented guys, when they did this great paper on how much each one of these broke up.
Yeah, that's a really good question. Yeah, I think we will do that. We have only a short paper about it now. We're going to do a larger one, and I'd be happy to just talk about those two. I mean, the other thing is the code is open source also. I know it's not a great way to see how much each thing helps, but we are, from now on, everything is visible, everything we do. Yeah.
Okay, so we'll try and venture.
Sure.
It's
Yeah.
just a good.
Yeah,
it
makes
was a
a
great
lot
paper from the Column guys, when
Yeah.
they first did C-Store.
Yeah, I can put you in touch with the people who did this stuff, because they kept track as they went along. Yeah.
You said RDD, resilient.
Yes.
So explain resilient.
Yeah.
What happens when the machine goes down?
So yeah, so the way, so we rebuild data by tracking the operations you used to build it, and you kind of transparently see the same data again next time you try to access it. As long as the underlying, the base data you start with is still available, so for example, HDFS still has a few replicas of that data, we'll rebuild it. It's kind of the same way that in MapReduce, if you lose the output of a map task, it will run another map task to build that data again. Yeah. We have actually quite a bit more written up about this part. Yeah.
What about my outputs?
Yeah, outputs.
So you're saying I have to do the work to persist them on disk. I can't just leave them in cache for my later computations?
You can leave them in cache. Well, anything, we can rebuild any data set again as long as the source data is still available, you haven't deleted the file in HDFS. If you want to save output, you can, of course, also save it to HDFS. Yeah.
But not to the cache.
Yeah. So you could, I guess, save it. You could actually, right now, you can't have it in the cache and replicate it, but that's actually something you'll have in the future, too. Yeah.
Thank you.
Yeah.
Hi. Are there any major features of Hive that do not work in Shark or cache mode?
Yeah. I should have put a slide with those. So there are a few things. there are mostly some esoteric features, like some weird things that happen when you have like a join, some types of outer joins. But the biggest one right now is add file, which is to ship like a script with your job. And we're working on finishing that pretty soon. And we do have, on the web page, I think we have a more detailed list of what's there and what isn't.
Can you give a little bit of details about how would Spark work with Yarn or on top of Yarn? And would you be able to combine a Hadoop job with a Spark job?
Yeah, so with Yarn, you'll be able to launch a Spark job, like submit a jar, or hopefully also launch an interactive session. And to share data with Hadoop, you'll have to do it through HDFS. But you can, in Spark, there's like a save operator, which you can use to save a file to HDFS, and then you can read it in MapReduce. So that's how it'll work. It will run, it's not, so Yarn just launches processes that will execute Spark. It doesn't know about what's happening inside.
Any timeline?
Any timeline, yeah. So this, I think within a month, this will be available in a dev branch. It's like halfway done. There is a branch with it, but we haven't had time to finish it yet. But it's very high on the priority list. Yeah.
Hi, a question about Shark.
Yeah.
What happens if you try to load multiple tables in memory?
Yeah, when you load multiple tables in memory, there's basically a least recently used cache replacement, and the things that don't fit anymore will fall out to disk. So that's what it does. So you'll still be able to run queries on them, but they may not be as fast once they've fallen out.
Does Shark use the same memory which the JVM allocates to job tracker, or is it outside?
So Shark is basically Spark and Shark only have one process on each node, like one executor process. So it's one big JVM, and it has its own memory both for executing code and caching stuff.
Okay.
Yeah. Okay, well, thanks. Other questions? Okay. Yeah, sure. Okay, thanks a lot. Yeah.